All right. Welcome all and Happy New Year. Thank you all for coming to our first RAL seminar of 2025. And it's an honor to represent one of our own talented members. Many of you here know Rajesh pretty well as a tireless and successful scientist that works in a variety of areas, including air quality prediction, remote sensing, and he's also been serving heroically as interim deputy director. And on top of that, I think we can all relate to the fact that he's a patient and kind mentor to many of us on many of the projects he shares with our lab, and an inspiring example. So for those of you who know Rajesh really well or haven't met him, I'll go through a few of his notes from his biography, but I can only mention a few things. So going back to where he got his PhD, that was done at University of Hamburg back in 2012 in atmospheric chemistry modeling. At that time, he was also a visiting scientist at Max Planck. And before that, he came from the Delhi region, where he did his bachelor's degree in science at IB College in Panipat, and has got a physics degree, master's degree at Kurukshetra University in India in 2006. So after finishing up in Hamburg, he actually came here as an ASP postdoc in 2013 to 2014, and has worked his way up to project scientist 3 and interim director since then pretty rapidly. And just to looking over his CV, 125 peer-reviewed publications already and many on the way, with over 5,000 citations, which is really impressive. Many of you are aware he just was awarded the Royal Belgian Academy of Sciences Baron Nicolai Prize, and also the RAL Culture Award winner in late 2023. And really great for the lab, he's been involved with, as PI or co-PI on about $50 million worth of funding and research grants, lead developer of operational air quality forecast systems in New Delhi and in the US, and many other projects that he's taken the lead in or involved in. Also serves as the chair of RAL DEI and links committees. And just, again, too many accomplishments to list here, but with that, I'll happy to turn it over to Rajesh.
Yeah, thanks a lot, Chris. That was very, very nice introduction. I'm flattered. So thanks for putting all those facts together. Today, I'm going to talk about advancing air quality prediction, challenges, innovations, and future opportunities. And so this is briefly the outline of my talk. I will provide a historical perspective into how this air pollution field started, where are we at now, what are the challenges. I will speak about my observational as well as modeling contributions to this field. And then I will spend the last part of my presentation on some of the upcoming challenges that I see and the opportunities that those challenges bring together with them for us in the future. All right, so air pollution is a field. Air pollution is a topic that has attracted mankind's attention ever since we probably discovered fire. Even when we didn't have fire, we probably experienced it during natural wildfires. But the real air pollution research that started with the big smog events that affected North America and Europe kind of in the middle of 20th century. So this is a picture of a big smog, the first big smog episode from LA, 26 July 1943. And so it was a big shock for LA residents, because people believed that LA was the land of pure air. And if you had tuberculosis, you just moved to LA and you get cured. That was the belief at the time. So when this smog episode hit, people were confused what happened. And so, as is our nature, we try to kind of guess what is the cause for that. And so the first reaction is it's a chemical attack by Japan. It was the year of the Second World War. And so, but then, okay, very quickly people realized that it's not a chemical attack. And so then they blamed it to a street plant that was in a steel plant, sorry, not street plant. There was a plant in LA. Maybe that is the reason. And so they closed it, but the smoke still persisted. Then the mayor of the LA announced that we know what is the cause of this problem and we are going to solve it in 4 months, right? So politicians, and you can see, you can relate to this, even politicians today make such remarks that environmental problems are very easy to solve and they can get rid of them in like seconds or minutes or days. But it took Ari Hagen-Smith, who started sampling the LA air about 8 years to tell people that it is the chemicals coming out of their cars which was causing, and ozone was really the cause of smog. But these means it is not like that this was really the start of the air pollution research, but this got the community's attention. And NSF NCAR, together with the community, has done a lot of hard work in advancing our understanding of air pollution. That involves laboratory studies where we study chemical kinetics, how different molecules react with each other, taking that knowledge into the atmosphere, observing the atmosphere, coming up with basic fundamental understanding of what are the variabilities in the pollutants. We have launched satellites to observe pollution from the space because we cannot have air pollution monitors everywhere on the ground. And then all this knowledge that we have gained from laboratory studies, field campaigns, regular in situ monitoring, space-based observations, we have developed physical understanding of the processes that control air pollution. And we have put that into our models because then we can use these models to do a lot of things. We can use these models for air quality predictions, which is my area of research now. And in addition to the advances in our physical and chemical understanding of the atmosphere, the computational advances have been equally important. If there were no computational advances, we would not have been able to run the models in the way we can run them on our supercomputers now. So that we should not forget that. It's a combination of advances in the multiple fields that 8 years ago, we didn't know whether the smog was pollution or a chemical attack. And now we are in a position that we can predict how air pollution is going to change in the next 5 years or so. And we can make decisions based on that. We can predict how air quality will be in the future. So it's quite a revolution in my mind that we have gone through in this community. All right, so what happened to the LA problem? So this science has also informed long-term reduction of air pollution in LA. So this figure here shows long-term trends in kind of ozone and PM 2.5. So see, the ozone levels in 1960s in LA were 680 parts per billion. We do not see such type of ozone levels anywhere on the planet nowadays. And we have brought them down to close to maybe like 150 parts per billion, which is still very large. So we haven't solved the problem in 8 years, right? Our politicians wanted us to solve in 4 months. So it is a stubborn problem. It is not an easy problem to solve. But the scientific knowledge that we have, with that, we can reduce the magnitude of the problem. So it's a incremental advances that we have to make. So this is kind of just a background. This is a motivation for me that we should not be expecting very fast results when we are working on our science. We have to be patient. Generations have spent their time in trying to solve this problem. The problem is still there. And in the meantime, it has become a global threat. It is not a North America or Europe problem anymore, which it was in the middle of 20th century. And you can see here, like you can see photos like that. If you just Google air pollution, you would see many, many more cities in your search. And latest estimates are that more than 8 million people die prematurely because of air pollution. The economic losses associated are 5 trillion or more. And a lot of food is lost because of the exposure of crops to surface ozone. So it's a big problem. And this is the picture that actually keeps me motivated to wake up every day, work hard, and try to make progress toward solving this problem. So this was the motivation. This is still the motivation for me to continue working towards solving this problem. But now let me take you a little bit towards my background, how I really started in this field. And I really started with observations. My career begin in the Himalayas at a beautiful site, Nainital. So if you can see here the atmospheric lab, this used to be my office for 5 years, from 2006 to 2011. And this site, it is an astronomical site. They have these domes that you see, these are there, it houses one of biggest India's telescopes that are used for astronomical measurements. But then the Department of Science and Technology in India said, oh, we can really use this site to characterize the background atmospheric composition in northern India. And so they started hiring some atmospheric sciences people back in 2004. And my PhD supervisor, I will show his photo later in the presentation, he joined there in 2006. I joined there in 2006 as a PhD student, and we started first ozone observations at this site in 2006. So we had no other measurement of trace gases at that time on this site. And then over the 5 years of my time in Aries, I participated kind of in greenhouse gas sampling, VOC sampling. I did gas chromatography analysis of those VOC samples, measured black carbon, aerosol optical depth, meteorological parameters, aerosol size distributions. And then towards the end of my PhD, we also started launching ozone sondes, which still continue. They have more than a decade of ozone sonde observations there. And I visited this institution after 10 years recently when I was in India, and their infrastructure has grown so much. It is so good to see that the place where we started with the ozone monitor is one of the best atmospheric chemistry observatory in India. So what did I do with that observations? We started looking at those. And here you see the seasonal cycle of surface ozone at Nainital, kind of in these colored bars. Different colors are different years. And we compared that in these open circles with the ozone seasonal cycle at a high altitude site in Western India. And so immediately we could see that the ozone seasonal cycle is different in northern India compared to Western India. What was also very interesting is when you look at Northern America and Europe, you generally see a summertime maximum, and we have a summertime minimum, which is because of monsoon. So this was very clear that different parts of India have different ozone seasonal cycles. But what could be the reason for this increase in January to, say, May or early part of June? And so we thought, okay, atmosphere is getting warmer, so there may be more local ozone production that may be happening. And so we start to look at the diurnal variation of ozone, and we see zero daytime photochemical buildup of ozone. So for those who do not know about the ozone diurnal variability, generally if you are in an urban area, you get very low levels during night, and then you get a daytime peak because of the photochemical production. So it was not local production at Nainital which was causing this increase. So it has to be transported. And that was my first introduction to some sort of modeling. And that is when I started looking into backward air trajectory modeling. So what I did was, for the 3 years that I had measurements for, 2.5 years, sorry, I calculated a 10-day backward trajectory at Aries Nainital every 6 hours. And then I looked at some kind of seasonal climatological patterns. And so we could see that there are substantial changes in air masses that arrive at Nainital during that time. So we really had influence coming all the way up from Europe and maybe Northern Africa. Of course, it depends on how high the pollution gets mixed in the atmosphere during the winter time. And then in May, we had air mostly circulating over this northern Indian subcontinent. And then we had the monsoon. And then once the monsoon retreat, we still go back to those kind of recirculation of air masses over this northern Indian subcontinent. So I tried to look at the relationship between the residence time of air masses over this box and ozone that we observe at Nainital. Because if it is produced regionally, then there should be a positive relationship. And that's what we find. So we find a very strong positive relationship. It means that if the air mass is circulating over this region, which of course is very polluted, it has the Indo-Gangetic plain, then you cook up a lot of ozone in the air masses that arrive at Nainital, especially during spring. In the winter and in autumn, this slope is very small. So It could be just the background ozone at that altitude, which is about 2 kilometer high. But we get a strong contribution from the regional production of ozone at this site during spring. Another thing that happens during spring is the crop residue burning. You all hear about the Delhi pollution, but you hear it in October, November. Nobody talks about the springtime crop residue burning. And the reason is this, because during the springtime, we have a very deep boundary layer. All these emissions get mixed up very high, and you actually see a signal coming into the Himalayas, but you do not see an influence in Delhi. Whereas during the October-November period, and here you see kind of a smaller number of fire counts, because I only took the high confidence fire retrievals for this study. But anyway, in context of Nainital, it is the springtime crop residue burning that is most important. In context of Delhi, which we'll go to later, it is the fall burning. And so I classified the data based on the fire counts, based on black carbon observations into fire impacted periods versus the low fire activity period. And so you see ozone in black carbon in dashed, and you can see a clear shift from towards the right from low fire activity to the high fire impacted periods. And percentage change in increase in ozone because of this is about 34%, and percentage increase in black carbon and AOD, in black carbon is directly emitted, is about 150%. So I used these results, and then I kind of get another opportunity to kind of look at another type of model, a single column radiative transfer models, and calculated the radiative forcing using these observations. And there was significant cooling at the surface and top of the atmosphere because of these biomass burning influences, and because of that cooling, there was a warming in the atmosphere as black carbon was trapping more radiation. All right, so I did some more stuff at Nainital, but these were key highlights of my research there. But I started asking a lot of questions based on the knowledge that I gained from observations at Nainital. I already spoke about differences in seasonal cycle. You see Nainital is up there. You look at other sites like Delhi, it's when you just do monthly averages, it's very low. It doesn't mean that ozone at Delhi is very low. Probably if you look at the daytime ozone, that is higher than Nainital. But then what was the interesting thing is, so we had a springtime maximum in northern India, whether you look at Delhi, Pantnagar, or Nainital. But when you look at southern India, it's a wintertime maximum. And so that was one question that I wanted to answer. That was one of the motivations to switch to modeling. Then seasonal sources of air pollutions, means we were just looking at Nainital, how are they affecting the regional things. If this much pollution is going into the Himalayas, I call Nainital as a gateway of pollution measurements in the Himalayas. It's not just stopping at Nainital, it might be going further up into the Himalayas. What are the implications for Himalayan glaciers that feed more than 1 billion people in the region? Where does this pollution come from? How will air quality change in India in the future? And these were some of the questions that inspired me to kind of take up the modeling. And we had no one who knew modeling in Nainital. So thanks to Gabby and Mary, who had been my mentors, who accepted me as a student here at NCAR. So I came here in 2009 to get some training in WRF-Chem modeling. So they taught me how to kind of run WRF-Chem. And so here, I actually explored all those questions, but I'm going to show only some selected results here. And so I applied WRF-Chem to study the impact of a dust storm at Nainital. And so here you see in black the AeroNet AOD observations and the angstrom exponent, which tells us whether we have coarse particles or fine particles. And so WRF-Chem, after some tuning, was able to capture variations in both AOD and angstrom exponent. And then we could also capture the dust storm induced changes in the spatial distribution of MODIS AOD during that dust storm. And then we look at the radiative forcing of those dust particles, and it was similar to the conclusion that we had for biomass burning, that they cooled the surface and the top of the atmosphere, except over some parts of the Himalayas. Means, of course, when you have snow, the snow changes the albedo and the radiative transfer through the atmosphere. But mostly it was a cooling at the surface, cooling at the surface and top of the atmosphere, warming in the atmosphere. And we look at it in both short wave and long wave, and the net is kind of short wave plus long wave. The short wave and long wave signals are opposite, but the total effects are dominated by the short wave interactions of aerosols with radiation. Another interesting aspect of this dust storm was a decrease in surface ozone during that dust storm that we observed at Nainital. And so here in black, you see the daily average ozone values at Nainital from 13th April to 24th April, which was and so the dust storm period was 17 to 22nd. And so you run the model without dust, which is in orange, and we don't see any decrease in ozone at all. And so there are two ways dust aerosols can affect tropospheric chemistry. One is via photolysis, another is via heterogeneous chemistry. And so then did another experiment where we turned on the photolysis effects of dust aerosols, and you get a small decrease. You go from orange to green. And at that time, we did not have heterogeneous chemistry on dust aerosols implemented in WRF-Chem. So I implemented the heterogeneous chemistry in WRF-Chem. But then that heterogeneous chemistry, that also depends on relative humidity. So initial implementation that I did was without the relative humidity dependence, and which is the blue line here. So we simulate the decrease, but it is too strong. We go below the observations. And then finally, I implemented the relative humidity dependence, and then we get the best agreement between the model and observations. So similar for the nitrogen oxides here, you can see that the red line is closest to the observations. And this really actually highlights the need for improving the models. Means even though we have come a long way, we are able to predict air pollutions, we are able to develop products, but this figure actually highlights the importance of advancing our knowledge, representing that knowledge in the models, because people who work in air quality, they know that we use satellite retrievals or observations for inverse modeling of emissions. Now, if you do not have heterogeneous chemistry in the model, maybe we will do the inverse modeling with these levels. So we will end up having wrong emissions. And if you appropriately represent different processes in the model, that is when we will get the right answer. All right, and then I took up the future air quality projection project. This was kind of my last project in ACOM, or my last project of postdoc. I look at how air quality is going to change in South Asia. So I ran WRF-Chem for 10 years in the present day, 10 years in the future, under RCP 8.5 and RCP 6 scenario. And so here, the color scale is such that if you see green color, it means we are within the ambient air quality standards. So air quality is good there. If you see yellow, orange, or red, then it means we are violating. So you can see as we go from present day to future, irrespective of the scenario, the situation gets a lot more worse in RCP 8.5 scenario, which is kind of business as usual. RCP 6 scenario, which was the lowest air pollution emission pathway in RCP, it will stay the same as the present day condition. But when you look at PM 2.5, it is worse now, and it is going to stay the same in the future, irrespective of whether you follow RCP 8.5 or RCP 6. So this means India needs to work on more stringent emission control measures to improve their air quality. And so they realize that they have a national clean air program to reduce sequentially pollutions in like 20% steps or something like that. And that was the point where I transitioned to RAL. That was in 2015. And so as we know that RAL is Research Applications Laboratory. So it kind of pushed me to think a little bit about what type of applied or use-inspired actionable science that I can do within RAL. And so I had a lot of questions, fundamental science-related questions that I wanted to answer. But then I came to RAL and I started thinking about a parallel approach. And so basically, I thought, okay, maybe we can probably break this problem down into two different time scales. One is the short term, where we use short-term air quality predictions to protect public health from extreme air pollution episodes, because air quality predictions have errors due to parameterizations of processes, uncertainty in inputs. Maybe we can use data assimilation, statistical post-processing, AI/ML-based forecasting, which I recently added. It was not in my original thought process. And then the long-term measures, because ultimately mitigation is the solution to this problem. And so we need to generate information about how do we design permanent emission control strategies. What is the contribution of transboundary transport of air pollution? How future scenarios will affect the air quality. So these are all kind of long-term measures, and then I have listed some possible scientific approaches, including chemistry climate interactions, source attribution modeling, scenario analysis, etc. And then at that time, I also looked at RAL's expertise. Means RAL has a lot of expertise in post-processing, data assimilation, etc. So that allowed me to think, in addition to the expertise that I have in terms of air quality modeling, how do I work with colleagues in my lab in RAL and across NCAR to implement some of these approaches. And so these are my main NCAR collaborators, 2009 to present. So I'm sorry if I collaborate with you and your name is not on the list, but this is just the list of the main people that I have been working very closely with. I am hoping this list would keep growing, and I get an opportunity to work with so many wonderful colleagues at NCAR. So this was my first project in RAL. I was hired to look at the impact of assimilating AOD retrievals from the MODIS satellite on air quality predictions in the US. And so in this project, this is the work that I did during like 2016-17. And so here, whether you look at a diurnal scale or a daily average scale, observations are in black. CMAC predictions without assimilation is in red, and CMAC predictions with assimilation are in blue. While we do not take the model very close to the observation, this was really encouraging. But here, the magnitude of PM is very small. It's like we are talking about like 10 to 15 micrograms per meter cube of PM 2.5. We had an improvement of maybe 2 to 3 micrograms per meter cube on an average. But so this was like good amount of improvement for the PM 2.5 levels that we have in the US. And then, coincidentally, this thing happened. 8 November 2017, it is called Red Letter Day in the history of Delhi. Indian Medical Association declared a public health emergency, and they called the conditions equivalent to smoking 50 cigarettes a day. Delhi Chief Minister called the city a gas chamber. Maximum PM 2.5 concentration reached 1500 micrograms per meter cube. For reference, WHO air quality guideline for 24-hour average is 15 micrograms per meter cube. Annual average guideline is 5 micrograms per meter cube. And on average, a person loses 6.5 years of their life just because they are living in Delhi. So Sachin Gude, my friend from IITM, called me in 2017, and he said, we had this day, and I will show in the next slide, the predictions failed badly, and he said, can you help? And I said, oh, I just did I did this. I saw some improvement in PM 2.5 predictions, but those were very small. So we do not know whether the same data assimilation approach would work in India, but that is something that we can try. And so that kind of started our partnership. As I said, the air pollution forecasting system, this is 8 November 2017, the day when that episode happened, and look at the WRF-PM prediction during that day. So there was a huge gap, and India had been investing into the system for the last 5-7 years. And so they were under a lot of pressure why we are not able to get the air quality warning for this episode. And that kind of led to a race against time to develop a new air quality early warning system. So we just went based on what we saw in the US, very small increment. And so basically, our first conversation happened in December 2017. We sent a proposal to IITM to implement the chemical data assimilation system in February 2018. In March, the proposal was immediately accepted. and the secretary of the Ministry of Earth Sciences, he called me and he said, I need the system by October 10, 2018. I do not know what you have to do, but I need the system. Okay, so we started running. I told him we can develop a system, but we do not have enough time to test it. We can just do a preliminary testing. And we found in some encouraging results during that. And we actually went operational in October 2018, which was the deadline. And then in January 2019, we transitioned the system to IITM. And it has been operational there since then. So even though we put the system together in 6 months, there was a decade of learning and decade of hard work that went into my training because of the people present in the room and elsewhere. There is a lot of expertise that was available in IITM who were ready to take this system over. That was another decade of work. So I do not want people to think we can put together an air quality forecasting system from scratch in 6 months. There is a lot of hard work and patience that is required to do that. But did we improve? And so this is the result in blue after we implemented the chemical data assimilation system. We improved the predictions by up to 200 micrograms per meter cube. And so the decision makers were really happy. They said, oh, at least we get information about whether air pollution is going up or down. That is the information that we need. We need information about tendencies. And so they were very happy for the first year, but then they start realizing the remaining discrepancies in the system, and they get greedy and they tell you, oh, your system is not working at all. So you get back to that loop of where you have to continuously interact with stakeholders to understand what their needs are. The solutions that you develop, are those solutions matching their evolving needs or not? And I'll show some examples in the future. But anyway, this was a big success for us, and we are really proud of this system. The Delhi air quality, this information is used by the Commission for Air Quality Management, which is appointed by the Supreme Court of India. When there is polluted air forecast, then they restrict activities. When there is clean air forecast, they go back to normal operations. And so this system has an accuracy of about 80%. That is the calculation over the last 5 years. We have seen by doing some sensitivity experiments that these restrictions cut down the peak pollution by up to 20%. So we are really proud of this system, but then I will show you that some other things happened this last winter. India is not the only place where we do air quality forecasting. Together with CABI, I also set up a air quality forecasting system for CONUS, which is operational again since 2019. And this is our website. You can go on the website. You can get information about air quality prediction over the US. There is a lot of parameters on the website that you can look at. We have similar dashboards for similar information dissemination system for India. Shima and Carl are now developing another system for Eastern and Southern Africa. So the regions where we are trying to kind of scale this capability, that is also growing with time. Then another thing that we recently wrapped up is developing a long-term air quality reanalysis over the CONUS. And this is again like, okay, we know that the satellite data assimilation is helpful for air quality forecasting. Can it provide us better information also for the past episodes? We have heard about meteorological reanalysis. So the idea was, can we develop an air quality reanalysis? And so we have developed this. So here in this figure, you see trends in surface ozone, MDA8 ozone. Where is my pointer? In the top row. And in PM2.5 in the bottom row. Okay, so here is. So this panel is CMAC. This panel is the observations from air quality system. You can, if you see a dark blue color, it means the trend is statistically significant. If you see a light blue color, it means the trend is not statistically significant, but it is decreasing. And same thing for the red colors. So we are doing pretty well for ozone. We are also doing very well for PM2.5 in the eastern US in terms of capturing the trends. But we have large errors in the Pacific Northwest. And we know that it is because of the wildfires. There are so many uncertainties in the emission inventories. We do not understand very well how these plumes from wildfires evolve, etc. But I think overall, this is a good reanalysis that can be used to look at how air quality has been changing in different parts of the CONUS. And we have also put together an air quality dashboard, thanks to Jen Bonert and Forrest Lacey, who have actually come up with this dashboard. So you can go to this dashboard. I forgot to put the link. And you can look at the county level trends in ozone and PM 2.5 in your county for this time period. Initially, we generated the data until 2018, but we have extended it to 2020 under a CDC project. And now we have a new NASA project to extend this data set to 2025. You can also see in your county how many days air pollution has exceeded the threshold. And then we have also made this data set publicly available, and it has already been downloaded 77 times. We also have come up with a Python interface. If you are a medical professional, you do not know how to handle the NetCDF data, you can actually go on the dashboard and you can get the time series for your county in a text file. Then, if you remember my Delhi plots, you see that, okay, we improve with the data assimilation, but then we still have some gaps in there. And we do not quantify the uncertainty of prediction because it's only a deterministic prediction with a single member. So Stefano here, who is also in the room, along with Luca Delle Monache, they come up with a very innovative approach. It's called analog ensemble. And so basically what they try to do is they look at the current forecast, they go back in the past archive, select the corresponding observations, and then they develop an ensemble based on that observation. And so with this, you need only a single deterministic forecast, but you can generate an ensemble, and you can use the ensemble dispersion or spread as a measure of the uncertainty. And so we have been testing this technique for air quality predictions during wildfires. These are examples of some stations where kind of the CMAC is in red, analog ensemble is dotted, and black is the observation. And so you can see with the analog ensemble application, you can actually bias correct these forecasts. So this is a really powerful and very computationally efficient technique to post-process the deterministic predictions from air quality models and quantify their uncertainty at the same time. This approach is not only useful for air quality, they have tested it for multiple meteorological parameters, renewable energy forecasting, numerical weather predictions, and it works fairly well in most of the conditions. We are also trying a dynamical ensemble approach to air quality modeling, and Chris Rozoff, along with Paddy McCarthy, is leading this project. So in the dynamical ensemble, what we try to do is we try to run multiple members. So here we are trying to run a UFS ensemble, UFS with online CMAC, and we are perturbing initial conditions for meteorology, emissions from anthropogenic sources, biomass burning, lateral boundary conditions. We still haven't done this, but we plan to perturb SOA, deposition parameterizations. And then this is still ongoing work. But what we are trying to do is we will do raw ensemble evaluation. And we know that in this ensemble design, we are not going to capture all sources of uncertainties. So it is going to be an under-dispersive ensemble. So we are going to have to do some type of ensemble calibration. And right now we have about a 40-member ensemble that we have run so far. But it is not possible to run a 40-member ensemble in operations. So we have to do some type of down selection, and we are targeting about like a 10-member ensemble and then make that recommendation to NOAA so that they can actually put this in operations. So this is just kind of an initial result here showing bias in PM 2.5 as a function of forecast lead time. So here, different colors represent different fire emission inventories, and the dotted lines represent anthropogenic emission perturbations. So we use, in addition to NEI, we also drive one member with HTAP. And so you can see that the dotted and solid lines are closer to each other. And this is CONUS average plot. And so on a CONUS average scale, this is the September 2020, the wildest of wildfire months. And so you see on a CONUS average scale, you see that most of the differences in ensemble members are coming because of fire emission inventories, but we are doing a regional analysis where we are finding that anthropogenic emission uncertainties may be more important for Eastern US and fire are more important for Western US. And then finally, this is a quick analysis that Forrest Lacey did when WHO released the air quality guidelines 2-3 years ago, when they lowered their recommendation from 10 microgram per meter cube to 5 microgram per meter cube. So Forrest looked at like, okay, if we remove everybody from the planet, no humans living, and restore the climate back to 1850, and then what would be the areas that would exceed the old air quality guideline and the new air quality guideline. And so in this plot here, you see the old one, which is the 10 microgram per meter cube. So if no humans are living on the planet, even then the areas that are dominated by natural sources like dust and sea salt aerosols, they would still exceed 10 microgram per meter cube. And if you change it to 5 microgram per meter cube, then almost everybody will be living in a non-attainment area. So the new air quality guideline that the WHO had set, it has been set purely from an epidemiology perspective. The atmospheric perspective has not been taken into account into that design of the new standard. Another thing is it has implications for equity in the international arena. Means we know that the richer and developed countries, they provide support to developing countries for expanding infrastructure in their countries to address the environmental hazardous problems. So with the lowering of the standards, now the more richer countries, they would try to meet their standards first before they can go out and help other countries. So this also has the potential to deepen inequities at the international level. Okay, so I have 15 minutes left, but I will try to wrap up it in like next 5-7 minutes to leave some time for questions. So now I'm going to talk about some of the challenges that have come out of my last decade of research and the opportunities that I see to address them. So I said we are proud of the Delhi system. This is the near real-time evaluation of the last 2 months. So going from October 26 to December 22nd. You see observations in red and WRF-Chem in blue. And this is Delhi average, like average of 43 stations. So you can see that for most of the time, the red and blue lines, they are overlapping with each other. So goes well along with our 80% accuracy estimate. But then when it mattered the most, we failed in the last season. So October 12 to 18, that was the worst episode in the last 5 years. And our system was not even able to capture the tendencies correctly. Not even our system, they are looking at 10 different air quality forecasting systems, and everybody predicted an improvement in air quality during 12 to 18 November. And the pollution just kept building up and building up and up. And so this is one challenge, means you do not know what happened. You are doing everything that you were doing for the last 5 years, it was working, then all of a sudden what happened? And then we found, oops, wrong button here. And then your credibility is undermined immediately. And so this is a news article from 19th November, right after the episode, saying that India's decision-making capability in Delhi paralyzed because government's early warning system cannot work. So back to square one, where we started back in 2017. But this leads to new opportunities, and we found that the public changes behavior around the policy enforcements. For the 5 years, there has been a system in place, and there has been a lot of watch on farmers, like when they are burning. The government is using the MODI satellite to look at, or the VR satellite to look at how the fire activity is changing. And this is like some of the one-day snapshots of fire counts. The top row is 2019, the second is 2020, 2021. Let me use the marker. And so you see here that this is the overpass time of the VIIRS or MODI satellite. And if you look at 2019, okay, there is some fires happening outside the overpass time, but you can see the map here in general has been representative of what has been happening over the other hours. But this year, farmers shifted the burning practices to late in the evening. And so the satellite data here now is not representative of what is happening there at all. So all the forecasting system in the world, they take the information from this time, they assimilate the observation from this time, but if something has happened outside this window, nobody knows how to account for that. And so now there is an opportunity for us. Can we look at a suite of the satellite measurements, try to use the geostationary satellites that India has to come up with a product that provides us information about the diurnal variation of fire activity. And we have aging satellites now. Means you see that we are assimilating MODIS AOD that is very helpful for improving our air quality predictions. But MODIS is dying next year. And so we need a replacement. We are doing some tests with the VIIRS satellite data. We have a joint project with M3 and ACOM. We are trying to test assimilation of PACE AOD retrievals in MPAS to see if that provides better air quality forecast. And then the standard MODIS algorithm, it cannot retrieve during the smoky and cloudy conditions. And it was a very, very interesting event, this 12 to 18 November. So you see here on the first day, 12th November, you had smoke. Of course, you also had some clouds. And the next day, the whole region was in fog. And I was at IMD last week, and they said this kind of broke our empirical belief. So they said, a fog will always happen when the temperature is below 10 degrees Celsius. That is the thumb rule that they use in India Meteorological Department. And temperature during that episode was 18 degrees Celsius. So they have to rethink their empirical approaches. The air pollution is pushing not only the air quality managers to think about how to solve these problems, it is also pushing the weather community outside their envelope and see what they can do. So I list some of the opportunities there. I mentioned about looking at the new satellites that we are doing. Maybe we should develop an international collaboration with ISRO. So Peter Nell is here, Helen is here, they are satellite experts. ISRO has a lot of capabilities in that regard. Can we start a dialogue with ISRO and come up with a geostationary atmospheric composition satellite for South Asia, which is currently missing? And then if the satellites are not going to see during these conditions, India recently launched a mission MOSAM. MOSAM is the Hindi word for weather. And they are going to invest $237 million in the observing infrastructure in the next year. So can we come up with an observational design, a ground-based observational network that can then be assimilated into the models to better predict these type of events? And then the enforcements that result from our forecasting system, it led to environmental justice and equity challenges. We never thought about that. We thought, okay, it is going to do good for everybody, but then whenever there is a severe plus air pollution episode happening, the commission, first of all, puts a ban on construction activities. So this happened in 2021. So there was a ban for 3 to 4 days. And the labor union, they moved to Supreme Court. They said, we cannot put food on the table. So people working as daily wage workers in the construction industry, they are the least responsible for the pollution episodes that are happening. And they are suffering the most because of those air pollution episodes. So that is an environmental injustice issue. And then Supreme Court is now asking us to provide a more accurate third-day forecast rather than a first or second-day forecast. We know that atmosphere is a chaotic system. The accuracy of our forecast go down with time. But they said, we need to let people know 3 days in advance that these restrictions are coming. So we are more interested in more accurate third-day forecast rather than first or second-day forecast. So the user needs are challenging our fundamental understanding of the atmosphere. But this is really an opportunity for us to define kind of maybe a convergent science project. We have an NCAR convergent science program now. Can we come together? Can we engage farmers, different sectors of the public, policymakers, government, etc., to come up with a solution to this problem? End of WRF-PEM development and support. WRF-Chem is the heart of the air quality forecasting system in India, right? So now we are supporting, which means no new knowledge will be integrated in WRF-Chem. They can still keep using it for the next 5 years or so, but we will have better models. And so this challenge provides us an opportunity to co-develop our next generation air quality modeling system with end users. And so we are involving IITM in the design of our, when we are putting chemistry within MPAS. And we are working together with ACOM and NCAR on developing, implementing chemistry within MPAS. So that we recently submitted a proposal to NSF to build this system. One of the challenges for air quality forecasting, especially in the US, is we cannot predict future fire emissions. And so recently, with Pedro Jimenez as lead, we submitted a proposal to NOAA where we propose to couple the fire behavior modeling with the atmospheric chemistry so that we can dynamically represent fire emissions into the model and how they interact with the radiation and how that is going to affect the fire evolution itself. So the Delhi system is very, very popular in India. India has launched a smart city mission under which there are 100 cities identified to be as smart cities. And each of them need to have an air pollution forecasting system. And everybody is asking, can we have the Delhi system replicated? IITM cannot run 400-meter resolution air quality forecasting system in parallel. So we need to be innovative. We have to think about how can we do this. So we are looking at some of the machine learning approaches. This is just one example. This is a figure produced by Chris Rozoff. And so here you see that we have our WRF-Chem simulated PM2.5 in a 2-kilometer domain. And this is predicted by 2 different versions of convolutional neural network. So more or less they look similar. But like here we had a fire and then you had smaller predictions there. So we have to properly test and vet these machine learning based predictions. Can we use these for downscaling air quality forecast to higher resolution in different countries? And finally, means we do air quality because we worry about the impact of air pollution on health, right? But what is the optimal resolution of our models? At what resolution do we need to predict, simulate air quality so that they can be used in health studies? And so here we are looking at the impact of model resolution on PM2.5 and ozone here. So we did simulations from 12-kilometer and 4-kilometer domains. So this is our normal air quality forecasting system over the US. These results are over Colorado. So you can see a pretty strong positive relationship between ozone. But for PM2.5, when in the 4-kilometer domain, we simulate PM2.5 going up to 350 micrograms per meter cube, whereas in the 12-kilometer domain says it is 40 to 60. And that can have a large impact on how are you going to, what health impacts you will estimate based on that. So we have several multidisciplinary projects going on in this area where we are looking at the impacts of air pollution on health. We are working with looking not only at the physical health, but also at mental health in collaboration with a professor from Denver University. So that is another exciting opportunity that is resulting from this challenge. People are asking us, can you repeat your air quality reanalysis and do it at 1-kilometer resolution? So there is a lot of request of that sense. So with that, my take-home message, I know that I covered a lot of very different things into this presentation. And so every slide can be a presentation in itself. But my take-home message for you is that even though, so I think it is a tremendous time to be an air quality scientist. It is such an important problem. If we are able to contribute to solutions in this area, I think we will be doing a lot of good things for the society. And I think the advances in atmospheric chemistry have put us in a position where we can help the society now. But I think we should not forget the importance of the fundamental science that has brought us to this place. So it is imperative, in my opinion, that we continue advancing our fundamental understanding of science, continue improving our models, continue, if we are going into machine learning arena, build more accurate data sets for machine learning. And then finally, I would like to thank to all my sponsors, and particularly 6 people whose photos are here, who have played a key role in shaping my career. They have been my mentors. So thank you so much, everyone. And thank you. I'll take any questions.
Thank you for that wonderful overview of a lot of great science and applications. I'll go around the room for questions.
Yes, I really, really like your talk.
Thank you.
It's very, very good. Yeah. So I have many questions, but I will limit to 2. So one thing that struck me is that when you talk about air pollution and all the examples you show, it's ozone and aerosols or PM2.5, but not nitrogen dioxide.
Yes.
Nitrogen dioxide is a lot talked about as being the indicator.
Yes.
So why is that?
So from India's perspective, PM2.5 is the most important concern for them right now. Means they are not even looking at ozone, right? So I think we are taking kind of a sequential approach in addressing the air pollution problem. So we look at the most important pollutant first. When we get rid of that, then we go to the second one, then we go to the third one. And that is what has happened in, I think, in North America and Europe. We have cleaned up PM2.5. Now ozone is the problem. So we are trying to improve ozone now, and NO2 is the problem. I think we need a coordinated approach, a multi-pollutant approach, and I still see that missing. So I think it's not we are not trying to ignore NO2. It's just that PM2.5 is just so important that everything is focused on PM2.5 there.
Yeah, so one of the things that struck me when I look at the OMI nitrogen dioxide images, the first ones and also later, that India is very, very polluted, but on NO2 it's not sticking out, basically. So I was also thinking about maybe the emissions are really different, and that also indicates to another focus in your work, basically.
You raise a very important point, and this is something that we actually observed during the Indian Ocean experiment back in 1998. So when they looked at the outflow of India, and then what they found was NOx levels were very, very low, and CO and VOCs were very, very high. So the explanation that was there at that time, which is still valid for many parts of India, is that there is a lot of solid biomass burning, which is a low temperature combustion, gives a lot of CO and VOC emissions, but not a lot of NOx emissions, right? But things are changing now. Means India has adopted the same emission standards that Europe has. So we are going to see less particulate pollutions from the traffic sector, maybe more NOx pollution. So I think if we look at maybe CO to NO2 ratio in the OMI data, we probably should see some changing indicators in the recent years.
Okay. Ammonia was my second question. I didn't see it on the list of pollutants. And ammonia nitrate is an important aerosol, so that would have been a second question, but there will be more. So let's talk about it later.
Sounds good.
Okay, so we're at the top of the hour. We have time for one more question. And
so Rajesh, very nice talk. So one of the strategies that's been used for climate projection to interface with stakeholder communities is this idea of storyline approaches. And have you thought of incorporating storyline approaches for the purpose of air quality projections in India or other places that could then relate to potential mitigation options that the government might take? Because it seems like they're giving you requirements of your forecasting system. Why can't you be proactive to them and to say, this is what you need to do to reduce emissions and how per these storylines?
That's an excellent suggestion, Chris. It is not explored yet, but this is definitely a suggestion that we can make.
all right, unfortunately, we are at the top of the hour. I know people are busy, so we'll wrap it up here, but glad to take more discussion right now for those who can stick around, or you know where to find Rajesh.
Yeah.
Anyway, thank you very much for that wonderful presentation, and let's thank our speaker once more.